Hello everyone. I didn't do that for a while, but yeah, let's try to solve some problems from second division to the first round and talk about their solutions. Alright, problem A, diagonals. A square board with side N and K chips. We need to place chips in some cells. Diagonal is occupied if it contains at least one chip. Determine what is the minimum possible number of occupied diagonals among all placements of key chips. So we need to say what is the minimum number of diagonals so that they have at least k cells in total, and as diagonals we only consider only one direction of diagonals. Doesn't matter which one, but only one. We cannot use like main diagonal and the other one. So clearly we want to take diagonals with more cells, and like I think for this problem it should be fine to just take all the diagonals, sort them by the number of cells. You can even do it like on square time and find the answer, right? But we can probably do a bit better. We can say that there is one diagonal with n cells, and then two diagonals with n-1, n-2, n-3, and so on until there is one cell. So the list we will be going through is just n, n-1, n-1, n-2, n-2, and so on. So we can write some simple for cycle. So let's hard code the case when k is equal to 0. We need to do something special for one of two corner cases because, well, our for loop will just have 2n-1 iterations, but there are 2n possible answers, so we need to specially consider something. So if we start with 1, then the number of cells on each largest diagonal will be calculated as 2 times n minus I plus 1, right? Divided by 2 rounded down. Well, we should just check that it works for 1 and 2. For 1 it will be n, and for 2 it will be less than n. It will be 2n minus 2 plus 1 divided by 2, so it's n minus 1. So k is how many we want. That's how many we got. If k became non-positive, it means that we have enough now, so I is the answer. that's it. And we should return from this function. Yep. Hey boy, say hi to the viewers. Thank you, boy. Okay, problem B has two versions. Let's read statements of both. One difference is that the quantity of each flower is 1. Okay, I don't know what that means yet. And flowers, each flower is characterized by the number of petals. Flower with k petals costs k coins. Okay. The difference in the number of petals between the two flowers she will use in her bouquet should not exceed 1. So we can only use like k and k plus 1 for some value of k. At the same time, the girl wants to assemble a bouquet with the maximum possible number of petals. Unfortunately, she only has m coins. What is the maximum total number of petals she can assemble in the bouquet? Right, so we have some flowers with given number of petals. We want to choose some subset of them with sum of AI as big as possible but not exceeding m, and in that subset all the numbers should be different by at most 1. So like maximum minus minimum should be either 0, so all the numbers are equal, or 1. We have like smaller and larger, and they're different by 1. Okay, that's the easy version. And the hard version, instead of listing the number of petals for each flower, the number of petals and the quantity of flowers in the store is set for all types of flowers. Okay, so here we will be given n types of flowers. For every type we are given number of petals and how many flowers of the type we have. This actually might be a nicer version of the problem. So yeah, let's just solve this one, and then for B1 we will transform the input to this format and then just use the same solution. So here it is nicer because like it is guaranteed that the number of petals are different for different types, so they are already like compressed in the groups with the same number of petals, with the same type. Okay, so because we want number of petals to be like almost the same, we can actually try, well, all the possibilities. All the possibilities are either we just have one type and then we can try all the types, or we can have two types that are different by one. It still will be linear from n, right? We can okay, we need like n log n time to sort them. technically we don't need it. We can use something like hash map, but we will sort them because it's simpler. And then check like pairs of consecutive pairs. What is that? Okay, we'll check consecutive pairs. And so now we kind of need to solve two cases. One case is where there is just one type, and the second case where there are two types that are different by one. Okay, so with one, it's very simple, right? So we have k petals. There are just C flowers of that type. How many we will take? Well, if we take x, then x times k should be at most m, but also x should be at most c. And under those conditions, we want x to be as big as possible. So, okay, we just take x equal to minimum of c and m divided by k rounded down. Okay, cool. That's easy case. So the harder case would be we have C1 flowers with k petals, and we have C2 flowers with k plus 1 petals. So now if we take x of those and y of those, obviously x and y should be bounded by C1 and C2, and x times k plus y times k plus 1 should be bounded by m, and we also want to maximize it. So we want to get this number to be the largest possible that does not exceed m. What can we say? So now we have two parameters, so it's not that simple as it was before. But if we fix one of those parameters, it will be as simple as it was before. So, for example, if we fix x to be something, then y should be just minimum of, well, how many we have, and the upper bound we get from this inequality, which is like y should be at most m minus xk divided by k plus 1 rounded down. Or if we fix y, then the upper bound for x we will get from this inequality is y k plus 1 divided by k. Okay. The problem is we cannot just iterate over all possible values of x or y, but we can say the following. We can try x equal to c1 or y equal to c2 and just like update the answer while trying that. If x is not c1 and y is not c2, then, well, we also know that x and y should be strictly greater than 0, otherwise we already consider it when we consider just taking one type, right? So x and y, like they are kind of sandwiched between those limitations, but we can like individually consider all the cases where one of those inequalities is actually an equality. So like x equal to 0 or y equal to 0 we already considered here, and x equal to c1 and y equal to c2 we will just consider right now separately by hand. what happens if all those inequalities are strict? Well, what I'm saying is that we can try to like shift them, because we know that the number of petals are different by exactly 1. We can try to do the following. We can decrease x by 1 but increase y by 1. Those limitations will stay true, but this number will increase by exactly 1, right? We're decreasing this product by k, but increasing this product by k plus 1. So this number will be increased by exactly 1. And until we reach this limit, we can do it. So when we will stop, well, we're taking some option, then we're starting to like change it, decreasing x, increasing y. And we will stop when either x becomes 0, y becomes c2. Both of those cases we already considered, so we don't need to care about it now. Or this thing actually reaches the value m. So that's the situation we want to consider now. So we want to check if it is possible to choose x and y in these bounds such that the sum is exactly m. Okay, how to do that? Let's try to rewrite it. We will open those brackets and group xk and yk together. So it will be x plus y times k plus y equal to m. All right, so we want to choose x and y such that this is true. We can see that this equation like fixes y modulo k, because if we have this equation, we can take it modulo k. So if we take it modulo k, we will get that y should be the same as m modulo k. Okay, so let's try to initialize y is just m modulo k. Then we will see what x plus y should be equal to. What will happen if we want to take y greater than this minimum possible value? Well, we have to increase it by k every time, because it should stay the same modulo k, right? If we increase it, like from this equation, we will see that it decreases what we want x to be equal to. And so basically we want y to be the greatest possible number that is equal to m modulo k, is not exceeding c2, and also we want x to be non-negative, so y times k plus 1 should be at most m, right? Why I'm saying that I want y to be the greatest? Well, because well, actually what I want is to get x to be in these bounds. We start with something, x might be bigger. If it is smaller, then it's bad, because we know that we cannot make y smaller. So probably x is greater than c1, but when I will increase y, I will decrease x, and I want to like stop when x is in this segment. And like one of the ways to ensure that is to take the greatest value of y that satisfies our conditions. Like this one, and this one, because this guarantees that corresponding x will be non-negative. And since we know that that is the greatest value of y we can get, means that it corresponds to the smallest value of x. So we will just check if this condition is satisfied. If it is not, then it means that x is still greater than c1, but we cannot make it smaller. So we have to stop here. And like it was just impossible to get this condition satisfied exactly. So that is it. That is the solution for problem B2. To reiterate it once more, we choose. We try all the possibilities for K first as just by its own, just one type. Then we try two types that are consecutive and their values just different by one. And we try x to be c1, find corresponding y, and update the answer. We try y to be c2, find corresponding x, update the answer. And finally, we try y, which is like the greatest number that is at most c2, at most m divided by k plus 1, and have correct remainder modulo k. To do that, we will like find minimum of c2 and m divided by k plus 1, and then like find the greatest number which is not bigger but has the correct remainder modulo k. So we'll choose that y, find the corresponding x, and check that it is in the bounds that we want. That's our plan for problem B. Okay, so first step is try just one. The number we want is minimum of m divided by the type and how much of them we have. Now we are iterating through pairs. We should do that only if their types differ by one. Okay, let's use some. Let's use variable names that we used here. So k is first, c1 is ai second, c2 is ai plus 1 second. Right, so first we try x to be equal to c1. So if k multiplied by c1 is at most m, means that we can choose some number y. And it will be minimum of minus k times c1 divided by k plus 1 and c2, and update answer with k times c1 plus k plus 1 times y. If k plus 1 times c2 is at most m, now we fix y to be equal to c2, then we choose x to be minimum of m minus k plus 1 times c2 divided by k and c1, and update the answer. And finally set y to be minimum of c2 and m divided by k plus 1, and we want to find the greatest number that is not bigger than that but has a remainder the same remainder modulo k the same as m. So here's our remainder. If current remainder is at least d, that means that to get to exactly d we need to remove current remainder but at d. Otherwise we need to remove more than that. Basically, if we do that, we will get number with the correct remainder, but it will be bigger than previous value of y. So to get the same remainder but smaller number, we will subtract k. And after that we can get a number that is smaller than 0, which is bad. So we will not, if y is smaller than 0, that's bad. Otherwise, this is a valid value of y. We can calculate the corresponding value of x, which is m minus k plus 1 times y divided by k, right? But we know that it should be like exact division. This number should be already divisible by k, so let's check that. And if we're all good, then we can update answer with x times k plus y times k plus 1, but we know that it is equal to m. That's how we found them. So we should update the answer with m, and well, normally you would write like this, but you can just write equal to m, and then break if you want, because, well, answer cannot be greater than m. We're literally finding the greatest number that is not greater than m that can be answer. And now print it. I'm not sure what we should print if it's impossible to do anything. I guess we can always take nothing. So 0 is an okay value to start, but we should check the statement. Like with the story, like I wouldn't call 0 flowers a bouquet, so if we can't buy anything, maybe we should have print something special, but I guess not. Yeah. That is not correct. Whoa, that is some spectacular bullshit. Yeah, 49 is just greater than 20. That's not good. Right, because it should be first here. Right. Yeah, that looks fine. Right, so not to get B1, we need to correctly read this input. Like, no, this input. So basically we need to compress coordinates. There are different ways to do that. You can use like std map, but I will just read it in another array, sort it, and do pointers to find segments of equal elements, and then put them here. So we can write the function read that will transform the input in the format that we need. So that was the solution for problem B2. Now we need to read differently. Right, so instead of doing this, we will read numbers here, sort them, and find segments of equal values. And don't forget to, like, we wanted n to be the number of those groups, so that's what we need to put here. Technically I don't need to sort it again, it's already sorted because I used sort to to make this coordinate compression, but it's not bad. All right. That took a lot of time. Problem C. Have an array of integers. Let's make array A fair, make it non-decreasing. Can perform an act of justice. Okay. Index I, which will replace AI with AI squared. Interesting. So we can repeatedly apply squaring. Well, okay, this is kind of stupid, right? So what is the kind of problem with that? Why it is not just super obvious? The issue is that like if we have decreasing array in the beginning, like we start with I don't know, n plus 1, then n minus 1, and minus 2, and end with 2. So we don't have to square the first number. We want it to be as small as possible. Then we take the next number, it is smaller, so we have to square it at least once. And we have to square it until it becomes not less than the previous one. And well, then we go to the third one and so on. And like this greedy make sure that for every index we apply the least number of iterations. The problem with that is that they are kind of compounding. If we did squaring in the second position, then in the third position we need to be like greater than the square that we got here, and the numbers can become very, very big. And also it will take a lot of operations to get there. Actually, like the answer can be order of n square times log this, but that's irrelevant. So yeah, we need to deal with two issues. Like we cannot do all the operations, and also we do not want to work with like very big numbers that we will get if we will just do the actual squaring. The solution to that is that we don't actually need to do all of that. Like if we basically if we take two numbers and apply some times of like squaring, and we will get like some relation between those numbers. If we now apply another squaring to both of them, the relation will stay the same. If x is smaller than y, then x squared is smaller than y squared, and vice versa. And moreover, if we want to undo one squaring, basically like take square root, but we should think about it as like undoing a square operation. That is also true. Like if we had two numbers that like one is bigger than the other, and then we take square root of them, then the result of the first will be greater than the result of the second. So when we have two numbers and we want to, like, we know how many squarings we want to apply to the first one. Now we need to figure out how many squarings we apply to the second one to make it not less. we don't need to actually do all those squarings. We just need to start with those two numbers and do the thing. Like find the number of squarings we need. But we need to be like a bit careful here that if the left number is smaller, it can happen that after several squarings it is still smaller. So when we like trying to understand how many squares we need to apply to the second one to make it like just bigger, so like this number of squarings was not enough, but this is enough. We need to consider that this number can be negative. Like we can undo some squarings on the second number, even if it wasn't a square, like it will become like irrational number. It doesn't matter. We can just apply squarings to the left one until it stays smaller. And say that, okay, if we can do 3 squarings for the left number and it still stays smaller, but after the fourth one it becomes bigger, it means that if we do -4 squarings, which is like 4 square roots, the number will become smaller, the right one, but after -3 it is bigger. So the result is like -3 kind of, and if we applied like 20 squarings to the left number, and so now we need to apply -3 more, which means like apply 17 squarings, like 20 plus -3. But if it was like 1 squaring for the left number, and now we can apply -3 more, the result will be -2, but that's not possible. We're not allowed to do negative number of squarings. So here we will just say that it's 0. And yeah, that's it. So our algorithm is like fully online. It's just like one scan of the array, so I don't need to save it. So we start with the first element, and the number of squarings applied was 0. And then I go through the array, read the next element, and I'm like, okay, how much squarings I need to apply to y to make it not less than x? By that number, I should increase this current value. This number can be negative, but this number cannot be negative. If it became negative, it means that I need to make it 0. And then I add it to the answer. As you can see, I didn't create the variable for answer, and as I said, the answer can be quadratic of n, which is greater than 10 to the 10th power, so it doesn't fit in integer, so we need to have a long answer. And here, like, it is simple to do with just 2 cases. If our number is actually smaller, then we apply squarings until it becomes bigger. Also, I want these numbers to belong longs because I think they're bounded by 10 to the 6, right? So if I have 10 to the 6 and 10 to the 6 minus 1, when I apply a square to it, it will become like the order of 10 to the 12s, which doesn't fit in integer. Yeah, and if x is smaller than y, while it is smaller, I will square it and kind of do result minus minus, but the last squaring makes it strictly greater, which is not okay for me. So I need to undo it. For example, make plus plus here and return this. Okay. Oh, right. Yeah, there is a special case when it's impossible. If number is 1, we cannot do anything by squaring. So I guess it is easier to just check it here. Oh, like, I don't know. Okay, yeah. If x is 1, then, alright, I also forgot to say x equal to y. If x is 1, then I need to ignore it, so just do x equal to y and continue. But if y is equal to 1, then it's bad, and I have to just answer minus 1, but I haven't read all the numbers. Okay, that's not great. Read all the numbers and then print minus 1. Okay, that's the issue. Well, not very common one. Like it's common for me to try to show off and like not store the input. I think it's a really cool property of your solution if you're able to not store the input, just read it once and that's it. But yeah, if something like that happens, if there is like some alert condition when you just need to throw everything and say, okay, it's impossible, you need to not forget to read till the end of the input because there is multitest and you need to read it so you can solve the next case. Thankfully it wasn't sample, so if I forget to do that, the sample will break. Yeah. So big thanks to authors who were kind to show-offs like me who don't want to read all the input at once. Okay, problem D. You are a linguist studying a mysterious ancient language. Okay, so we're using only the first C letters, and C is to 18, interesting. What's a case? Okay, so there is something that is called a case, which is determined by the last letter of the word. So if two words have the same last letter, then they have the same case. And if they have different last letters, they have different cases. If the language does not have a case corresponding to some letter, it means that the word cannot end with this letter. That doesn't sound like a good thing to write in the statement. But okay, let's see. The length of each word is k or less. Okay. You have a single text written in this language. Unfortunately, the language is really ancient. Spaces between words are missing. All letters are uppercase. I wonder what is the minimum number of cases the language can have. What they are talking about. We're given a string, we need to split it in the into some strings of length at most k and minimize the number of different letters that can be lost. Is that it? This statement kinda sucks. I guess they wanted to make some joke about number of cases. What is it in Russian? The authors are Russian, right? Подержи. Okay, so they wanted to make some linguistic joke about I mean, I don't even know what's the right term in English. Maybe it's case, but in that case you need to drop the joke and don't do that. Like, if you have to write a statement in English which uses the word case not as something that can have different variants, like, you shouldn't keep the joke in the statement. It's just very confusing for everyone who's always like, I speak Russian and that is not helpful. It's still confusing. No, don't do that, authors. Okay, so the problem. We need to split a string into some words with length at most k. And minimize the number of different letters that are used as the last letter in the word. Okay, let's look at it differently. What if we fix the set of letters that can be lost? Then obviously we should cut after each such letter. We want all words to have length at most k. That's the only other condition. So we cannot cut after letters that we didn't include in our set of last letters. But we can cut after every letter that we did include in our set. And obviously it's always good to cut. Like, it's independent from everything else, so just do it. And we just want to check that there basically the answer will be the longest block of consecutive letters that are not in our set. Oh no, I mean the longest block of letters that are not in our set should be strictly less than k, because this block and plus the next letter will be a word, and it should have length at most k. Okay, so this is already a solution in time 2 to the power of c, just to try all the sets, times n, because we need to find the longest block. The sum of n does not exceed this, and the sum of 2 to the power of c does not exceed 2 to the power of 18. Okay. Well, for every for every position, like, it will be in the word somewhere. Maybe it's not the beginning of the word, but still, from that position, the distance to the next letter that is in our engine set must be at most k. So, okay, we can say that. So fix kind of left border of the string, but like just for every border, consider this border and consider what is the distance to the closest ending letter. Well, the problem is we don't know the set yet. We want to choose it, but for this border we can find the closest occurrence of every letter. We have just like 18 of them. So let's find for every border the next occurrence of every letter. That is done by scanline from right to left. Like, if we know those positions for this border, if we move it one to the left, then for every letter it will be the same except the one just next to us, like the one we changed basically. For it will be, well, here. Okay, so for every position we now have those like 18 positions where the next letter comes. So okay, I guess let's draw something. So here's the border, the string. And we're like, okay, here's the first letter, the second, the third, fourth. Well, obviously the first one will be just after this border, but for a picture it's just not very convenient to draw. Okay, so what do we want to say? Let's say we have chosen the set of ending letters as like this one and this one, and maybe some others that don't even appear on this suffix, like they appear only before. What will we say? Well, we will say, okay, for this to be a valid set, the distance of the closest of them to this border must be like at most k, depending on how you define distance, like it is strictly smaller or not greater. Okay, so how can we say it differently? Like for this border, like why did this happen for this set? Well, it happened for the set because this set did not include this first letter. Or maybe like, let's add one more. There was another. Did not include this letter, did not include this letter, but it included the next one. So what can we say? We can say that if the set doesn't include like those two letters, then well, okay, if this distance is less than k, then well, nothing but happen. But if it is greater than k, if the set did not include the letters here, then it's a bad set. It must include at least one. Okay, I guess I was trying to solve some like a bit harder problem. I keep forgetting that number k is constant. For example, I could calculate for every set of ending letters, I can calculate the maximum length. It is not that hard. But this problem is easier. We can just say, okay, like what I said before. We should make sure that the set of ending letters, for the set of ending letters we choose, there doesn't exist a segment of length k or more that doesn't include any of those letters. Why is that? Well, because if that segment exists, so this segment of length k, which doesn't include any of our ending letters, well, it means that if we look at the word, like, okay, there will be a word that contains all of them, and also it must end somewhere after it in some ending letter. And so this word has length strictly more than k. So that's bad. Okay. If that doesn't happen, then the chosen set is good, because if we cut after every possible ending letter, no word will have more than k letters. Right. Obviously, the set should include the last letter of the text that is given to us. That's clear. Right. So we can reformulate the problem as follows. Let's look at all the segments of length k of consecutive letters. Look at the set of letters on each of such segments, and our chosen set must intersect with every one of those. So now the problem can be restated as follows. We have some sets of letters. I write Sn, but it's clearly Sn minus k plus 1. It just doesn't matter. Like if n is the length of the text that is given to us, and we are moving, like we have the sliding window of size k, then we will have n minus k plus 1 different positions of the sliding window. Let's just call this number n prime. That's the number of sets we are considering. So we have those sets of letters. We need to choose set A such that A intersects with every one of those. This is not empty for every I. And we want the size of the set to be minimum. Okay, to do that, we'll say, okay, for every Si, the what is the word? Oh. All elements that are not in the set. But how does it called? Totally blanked. Complement, the complement set. The complement set of this. So basically saying that intersection is not empty is the same as saying that it is not true that A is a subset of complement. Not subset of complement. Not subset of complement means that there is an element in A that is not in complement, which means that it is in the original set. So these two things are the same. Okay, let's say that the complement of Si is a bad set, and just mark it as bad. And it's clear if some set is bad, then all the subsets are also bad. So now we have marked all of those as bad. Now we need to mark all smaller sets, all of their subsets as bad. That can be done by very simple DP. Just go from large masks to small, and if something is marked, you try to remove each element and mark set without that element as also bad. That way you will mark every subset, because every subset can be constructed as take this and remove elements in some order. Remove the elements you don't want. So after we do that, we have marked all the bad sets. All the sets that are not marked are good, and we just need to take the one with smallest size, smallest pop count, and that will be the answer. Okay, so now we need to do a sliding window and maintain a mask of characters that appear in that window. How to do that? Well, it is not easy to maintain a mask because when we remove the symbol, it is hard to say whether uh, it is still there or we removed the last occurrence and now it is not in the mask. So instead we will maintain the count for every symbol inside the window, and well, if it reaches 0 then we have no symbols left, and since the limitations are small here, it's okay to do like for every mask, just for every position of sliding window, just look at all the symbols. For everyone we will have the count, but if we wanted we could maintain the mask or like every other characteristic we wanted. Like for example, we could maintain like sum of squares of characters that appear, just like if the count was 0 and we increased it to non-zero, it means that the character was not in the set before, but now it is. So we need to like turn it on. And if we decreased the count and it became 0, it means that it wasn't no, it was in the set before, but now it isn't, so we need to turn it off. Okay, let's write it in the right way, just because I can. So first we initialize it for the leftmost position of the sliding window. It's capital letters. Okay. So then say that this mask is bad. And then for then slide the window. Right, so we remove the character that was removed from the window. We add the character that was added to the window, and mark the mask as bad. So when we do add one, we increase the counter, but also if the counter was 0, then we need to turn on the corresponding bit in the mask. It should have been switched off before that, so let's say that we flip it. Like it doesn't matter here, but it will be easier to write the same when we want to turn it off than to say and with mask without this bit. It's cumbersome. So here we do minus minus, and if it became 0, I need to remove it from the mask. It should have been on before, so if I flip it, it is now off. Okay, so now I marked all the masks. Oh, actually I need to mark the complement. Okay. Done. So yeah, because I'm flipping bits every time. If like at the start I'm saying that okay, now mask stores all the characters that do not appear in the window, then these functions are still correct, but now like mask has the opposite meaning. So now I'm marking the complements of what's inside, so what's not inside. Great. And now do the simple DP I was talking about. If this mask is marked as bad, then we need to try to remove the element from the mask and say that the result is also a bad mask. Okay. Right, and also the last symbol should also be good, so we can just say that the last symbol is its own set, such that the resulting set should not be a subset of its complement. So I just need to say that bed of masks or something like this is one. Okay. Okay, so now if the mask is not bad, it means that it is good, and I should update the answer with the pop count of that mask. We can just use built-in pop count. And that's it. Problem E with two subtasks again. This is easy version, the only difference constraints on T and N. Okay, so here it's 2000, here it's okay. So we have some 2N knights. They're sitting at the desks in pairs, but in a circle. Okay, so we have like array of n pairs of elements, but they're on like a circular array, probably. Each knight has intelligence, which can be measured by an integer. Okay. Arthur wants the maximal difference in total intelligence over all pairs to be as small as possible. So we calculate the sum in every pair and then take maximum minus minimum. Okay. However, the code of chivalry only allows swapping the opposite knights in the circle, so Arthur can simultaneously perform, well, swap. Yeah, Arthur can perform a swap of knights at the opposite ends. What is the best result he can achieve? Okay. I think that it should be clear that even and odd values of n are very different for this problem. Why is that? Well, because if n is even, then, well, okay, never mind. If n is even, for example, n equal to 6 here, each pair has the opposite pair. And so we can swap this and this, we can swap this and this. And they're inside one pair. So what we can do basically is for if we fix like this and this guy like this, we can choose whether we want this guy to sit with this one or with this one. If we want with this one, then just don't do anything. Otherwise, we should swap them, and this one will get this one in pair, and this one will get this one. And then we do it independently for every pair. So we want to minimize maximum minus minimum, but the sum of values is fixed. So let's say that the sum, okay, have a sum, right? If we divide the sum by n, we will get the average of intellect values of pairs. And since the sum is constant and n is also constant, it means that average is constant. And what we know about average is that it is not greater than maximum and not smaller than minimum. So we want to minimize this value, maximum minus minimum, but we know that between them there will be average, which is fixed. It is just a number that we can calculate. It's just the sum of everything divided by n. It is a number. And we cannot do anything about it. And that means that, well, technically we can just try to minimize maximum and maximize minimum. Well, it is just like, it is true in general. But when we have something in between, it's kind of easier to look at. And so in this case, when n is even, okay, for every pair of opposite tables, we need to make some choice. And we will make a choice that minimizes maximum and maximizes minimum. And because all of the shenanigans with average is true for just these four guys and two tables, it's also true that for them maximum and minimum that they contribute, they have average between, and moreover just sum of maximum and minimum is constant, so minimizing maximum will maximize minimum just automatically. So yeah, if n is even, it's just very simple. Just greedily choose the best option for every pair of opposite tables, and that's it. What happens when n is odd? Well, I would guess that something not great is happening. So this pair is matched, this, this. All of those lines should have passed through the center of the circle. Also, it was supposed to be a circle. Yeah, I'm not great at drawing circles. Is the lesson we learned here, I guess. So we can swap yeah, I hope you see the difference. That like we are swapping the guys that are like one of the, if we rotate the circle, if we move through the circle, when we move from 1 to 2, 1 was swappable with 6, 2 is swappable with 7, and 1 and 2 are on the same table, but 6 and 7 are not. So yeah, it's very, very different. Let's draw in smaller case. Radiation. It's interesting that like the first can be matched with a lot of different knights. Well, not a lot, actually, just 4 of them. So if he stays here, he can be matched with, well, obviously the second, but also with the fifth, because we can swap them. So we can match 1, 2, 1, 5. But if we swap here, it can be matched with 3, but also we can swap this to 1 will be matched with 6. Which might look like, well, all of them except the well, himself and the one we are swapping him with. But actually it will be just for any odd n that is greater than 1. Well, because there are just two positions that he can take, and for every of those two positions there is one neighbor, and for that neighboring seat there are two possible knights. So for example here it will be matched with 2 or with 7 if it's here, or if it's here then with 5 or with 10. So I don't know how to solve this at all. So when I don't know how to solve, I try to, well, first I need to come up with some polynomial solution. I know that the limitations are big, but let's just ignore that for a while. Let's try to come up with some polynomial solution. So I know that for every knight there are just 4 others with whom he might be matched. So I can only have 2 times n possible pairs. Well, you might say that, well, we have, oh no, it's, yeah. You might say it's 4n and that will be true, but, well, you actually might say that it's 8n. And that's not true. Like, we have 2n knights, and each one of them can have 4 different pairings, but we count each pairing twice, right? Like, we understand that the first one can sit with the second one, but we will also understand that the second one can sit with the first one. So we have 2n knights and 4 possible pairing for each knight. That's 8n, but actually we counted every pairing 2 times, so the actual number of pairs is 4n. That's possible number of that's the number of pairings that are possible. Let's find all those pairings, calculate the sums of their intelligences, and sort them. If we fix minimum and maximum, we just saying, okay, everything that is between minimum and maximum are allowed, everything else is not allowed. So we have those 4n pairings, we have sorted them on number line. Then we are saying, okay, like, this is a good segment, this will be our minimum, this will be our maximum, and now the problem is a decision problem. Is it possible to swap the knights such that every pair is inside this segment? Now let's try to solve this decision problem. If I can solve the decision problem in some reasonable time, then I can, for example, do like 2 pointers on minimum maximum, or just like fix minimum and binary search maximum. So to get the solution for the easy subtask, I need like linear-ish solution for the decision problem. So I have the segment. What is it possible to get what I want? Decision problem. Well, I guess it should be some kind of DP. I will fix the decision whether I want to swap this like last pair, and then I will go around the circle, and I know the decision I made for the last pair. I will also store in the DP state what decision I made for the previous pair. And go like this. So when I'm looking at some pair, like for example, okay, there will be two types of pairs. Well, let's look on the bigger example. It will be more telling. So here I need to satisfy this pair. I know that I need to put it inside this segment. So do I have to swap them? Do I have to not swap them? Okay, then I move to the next pair. Now this seat is in the new pair, so we don't have to do anything for it now. But for this table, we will now choose the second knight on this table. We need to make sure that this table is also good. And yeah, so we're doing dynamic programming, position, and did we swap the knights in the last position? This is linear number of states and constant number of transitions, and the DP state is just a boolean. All right, that is n square solution right here. So I'm doing 2 pointers on this thingy, then inside I'm doing linear DP, n square with some big constant, but it should be okay, right? Sum of n up to 2000. It's a good n square. The constant is somewhat big, but like not insane. Maybe it's like 32, I don't know. It's fine. Right, but this solution certainly have no chances to be updated to work here. Maybe I don't need DP, right? I know which I know which pairs are allowed to sit at the same table, right? That's why we did this. Like, this segment is allowed, so yeah, for pairs that are inside this segment, and they're good, others are bad. And now I just need to say whether I can achieve configuration where all the pairs are good. Maybe it's just a property of like some, I don't know, some graph must be connected to something. I can check it with linear DP, but technically it shouldn't be. Like, maybe I want something. So I'm tempted to draw edges like this, like all the time. So those are edges that I can swap. And then I want to draw edges between the pairs that are good, that are inside the segment I'm checking. Why am I tempted to do that? Because, like, well, what is the stupidest configuration that is good? Well, if they're already sitting well, then it's okay. But well, in this configuration, if we look at the edges I have drawn, I want to say that it's a cycle. So if it started at 1, then 6, 5, 10, 9, 4, 3, 8, 7, 2, 1. Which is different from when n was even. When n was even, it was like a lot of small cycles, and over 2 small cycles, to be precise. And here they're in one big cycle. So maybe I need it to be one big cycle. What will happen if I, like, I don't know, swap 1 and 6? Then 6 will be with 2, and 1 will be with 5, right? So 1 with 5. And like, those pairs must be good. I get 1, 6, 2, 7, 8, 3, 9, 10, 5, 1. So it's still a cycle. I mean, yeah. If I just if I look at the cycle not as like numbers of knights but numbers of positions, that is always the cycle I want to have. It just can happen that like those two are swapped, those two are swapped, and so on. So but what are the other possible edges I can have with this one? For example, this one, there's 2, there is 5. But also 2 can be swapped with 7, and 5 can be swapped with 10. The question is, like, is it true that I just need connectivity? If it is just connectivity, then I will be good. I think. It won't be super easy to implement. Certainly not in 12 minutes. Well, okay. I certainly don't have enough time to get the last one accepted, at least with understanding what I'm doing. But I can try to write Ivan. It probably probably I won't be able to write it in 12 minutes either, but we can try. If n is even, so I'm just saying that so the minimum is inf, the maximum is 0. So those are the values of 4 guys in the pair of opposite tables. and I can get either x1 y1 and x2 y2, or x1 y2 and x2 y1. Choosing the best of the pairs and updating the answer. That's it. Okay, now the hard case. So I found all the pairs that can be, sorted them by value, and now I'm doing 2 pointers. Okay, now I want to check if it is possible to construct correct setting using only pairs with values from L to R. That? Yeah, okay. In 4 minutes, yeah, there is no chance I can do that. That's a hard problem. I actually don't know. I don't know how to solve the hard version, and for the easy version, like I would need some time to implement that. Like at least 20 minutes, maybe even more. Well, alright. I mean, I spent way too much time trying to explain easy problems. So it's alright. Problem C is kind of like I remember like at quadrant problem with the same general idea of applying the same function, the same monotonic function, and making and make the array non-decreasing in smallest number of operations. And they just had like a different function, but it's the function is not really important for the problem. Like the solution is just apply it. So yeah, this is kind of a copy of that problem. Well, I mean, that problem had a harder function, so it's not bad by any means, but like it's a bit well known. I guess there was also a problem where you just multiply by 2 instead of squaring. That doesn't change anything in terms of solving. Well, okay, it changes that. Well, no, the numbers could be big in that one too. So it's the same problem. Yeah, and in problem D, I really don't like the English statement, like especially the use of the word case, which has strong meaning in mathematics and in programming. It is very hard to change it to like ooga booga, the word without meaning. Very hard to stop seeing. And other than that, it's an again problem. And problem E, I don't know how to solve. That's kind of cool. Yes, thanks for watching. Bye.